and welcome to this section 5.4, dividing polynomials. So in this section, we're going to use properties of exponents to divide polynomials. This should be a little bit of a reminder from what you've seen before. And then something new would be using synthetic division to divide polynomials. And then we're going to use synthetic division to help us completely factor higher degree polynomials. All right, so let's recap regular old division. Well, I forgot to mention, the reason we're doing this is before we were able to find all the zeros of a polynomial by factoring it and looking at the linear factors. But what if you don't know how to factor the polynomial? Well, this answers that question. So we're going to learn how to divide them. Let's review our division terminology. Let's just do a quick division problem. 51/36 divided by 3. So remember, we take the 3 into the 5 one time. 21, 7 times, 21, 3 comes down, 1 time, minus 3, 0, 6 comes down, 2 times, and that's a 7. So 6, and then that's 0. Okay, I kind of wrote over my words, but that's okay. Remember what the dividend is. The dividend is what you want divided, or if you're writing it as a fraction, it's the numerator. So in this case, 51/36 is the dividend. The divisor is what you're dividing by. So in this case, it is 3. It's also the denominator if you write it as a fraction. The quotient is the result you obtain after doing long division. So in this case, our quotient was 1712. And the remainder is any of the stuff left over. So if this had not been divisible by 3, that could have been a 1 or a 2. So our remainder in this case is 0. So those are all words that we need to remember how to use. All right. Let's practice using polynomial division, and this is just going to be using properties of exponents. So if we want w to the fourth divided by w squared, I'm going to write it as a fraction, w to the fourth over w squared. And hopefully remember from our properties of exponents that this is subtraction. We can also kind of remind ourselves, because w to the fourth is like w times itself 4 times, and w squared is w times itself twice. These guys would cancel, right? And we get w squared. You might also remember it's w to the 4 minus 2. That was a property of exponents. That gives us w squared also. Well, okay, let's try a little bit harder one. What if we have k to the 9th plus 2k to the 7th minus k to the 4th divided by k cubed? Well, when the divisor is a single term, like in this case k cubed, remember, we can break this up into 3 separate fractions. We can make it as k to the 9th over k cubed plus 2k to the 7th over k cubed minus k to the 4th over k cubed. Now, if it was the other way around and we had the 3-term expression in the denominator, we would not be able to do this. It's only when you have a single term in the denominator. Well, k to the 9th divided by k cubed is k to the 6th, 9 minus 3. Oh, good. Hang on, I have a battery right here. A charger, I mean, here we go. Let's get charged. Right in the middle of my video, of course. There we go. All right, so that'd be k to the 6th plus 2k to the 7 minus 3 is 4th minus k to the 4 minus 3 is k. All right, and let's just take 1 minute to remember what this is actually telling us when we do a division problem. If we know that k to the 9th plus 2k to the 7th minus k to the 4th divided by k cubed is equal to k to the 6th plus 2k to the 4th minus k, that also means that this guy, k to the 6th plus 2k to the 4th minus k times k cubed will give us our original value. I'm going to let you guys check that on your own, but I think you can see pretty quick that's going to be k to the 9th, 2k to the 7th, minus k to the 4th. All right. So that is remembering our properties of exponents to do some polynomial division when we're dividing by a single term. All right, let's talk some more about some other types of polynomial division. There is a process called polynomial long division in which you can divide any polynomial by any other polynomial of lesser degree. It is really more than we need for Math 111. You will come across this again in maybe like Math 252, but I think I'm going to leave it for you guys that are going to 252 to discover that process. Then we're just going to do a simplified process called synthetic division. if you are interested in polynomial long division, you can find some videos that will go through that with you. So what is synthetic division? Synthetic division is a special way of dividing polynomials when you're dividing by a linear factor. It only works when you're dividing by a linear factor. Okay? So whose leading coefficient is 1? So it has to be something like x minus some number, right? X minus k. I already had that written down. I'm thinking ahead of myself. So the divisor has to be the form x minus k, where k is any real number. And the way you set up synthetic division is you use a little chart like this. And across the top of the chart, you put your coefficients of your dividend, the numerator number. You put the coefficients across the top in order of decreasing degree. So 5x squared, I put a 5 here from the 5x squared, a minus 3 here for the x, and a minus 36 for the constant term. If there is any term missing, like if there had been just no x term, you would have to fill in a 0 for the coefficient. We'll do one like that. And then x minus 3, you put 3, the number that is the 0 of the function. Remember we talked about that if x minus 3 is a factor, 3 is the 0. You want that x minus number, the actual k, to go in that spot. Then the first thing you do is you bring down the 5. Okay. You multiply the 3 by the 5, and that goes here, and that becomes 15. Add down. That becomes 12. Minus 3 plus 15 is 12. Multiply the 12 by the 3 and gives you 36. Add down, and you should get 0. If you got 0, that means it divided into the divisor, divided into the dividend evenly. Okay? And in fact, these are your coefficients on your quotient. So what does that mean? It means that if I take x minus 3, which is what I divided by, and I multiply it by 5x plus 12, right? This is my constant term. This is my x term, and you always go up like that. I multiply it by 5x plus 12. I'm going to get back to my original value, 5x squared minus 3x minus 36. All right? So that is synthetic division. Let's do another practice problem. All right, let's do a little bit harder one. This one is same idea, synthetic division. We're just going to do the division. We'll talk about what we use it for in a minute. So let's set up the synthetic division problem. Set up my little chart. And I start with my leading coefficient, and which is negative 9 in this case. Negative 9, that's my coefficient on w to the 4th, plus 10w cubed, plus 7w squared. Now there is no w term, so I need to put the 0 in as a placeholder. Okay, so that's my placeholder, because it's really plus 0w if we wanted to write that out, minus 6. Okay, and then w minus 1, so the 1 goes here. Remember, it's whatever you're subtracting goes there. This guy comes down, that's negative 9. Negative 9 times 1, negative 9. Add down, get 1. 1 times 1 is 1. 7 plus 1 is 8. 8 times 1 is 8. 0 plus 8 is 8. 8 times 1 is 8. Add down, and I get 2 as my remainder. What this means is this does not divide evenly. Does not divide evenly. Does not divide evenly into that big polynomial. All right, so that is how you do synthetic division. Now let's talk about how we use synthetic division to help us completely factor higher degree polynomials. So let's look at this function, 6x to the cubed minus 49x squared plus 46x plus 21, and here's a graph of it. From the graph, we can see one of the zeros looks like it's 7 right on the graph, but it's hard to see the other two. They look like they're fractional, and maybe we can guess, but we can actually use this 1 0 to reduce our cubic polynomial to a quadratic, and then we can just factor in the normal way. So let's go ahead and try. What we're going to do is we're going to notice that x equals 7 is a 0. So that means x minus 7 must be a linear factor. If 7 is a 0, then x minus 7 must be a linear factor. And we talked about that in the last video, how that all worked out. So what we're going to do now is we're going to take 6x to the cubed minus 49x squared plus 46x plus 21, and we're going to divide it by x minus 7. And that will be giving us a quadratic term, which we can factor in the normal way. So let's use synthetic division to divide these two. So 6x cubed minus 49x squared plus 46x plus 21. And then we put the 7 there because remember it's x minus x minus is 0. So this guy is the 0 usually, 0. Well, it looks like I'm saying that is 0, but it is a 0 or a root, or a horizontal intercept. All right, we bring down the 6. 7 times 6 is 42. Add down, -7. -7 times 7 is -49. Add down, -3. -3 times 7 is -21. And good, we got a remainder of 0, which we were expecting, because we know that if 7 is a 0, x minus 7 is a linear factor and should divide evenly into this term. So what does this tell us? That looks like 0.6, but it's actually just 6. This tells us that x minus 7, this is my constant term, this is my x term, this is my x squared term, times 6x squared minus 7x minus 3 is equal to my original polynomial. 6x cubed minus 49x squared plus 46x plus 21. All right, so now all we need to factor is this guy. How many people need a refresher on how to factor? Hopefully, not too many of you. I like to do the AC method of factoring. All right, so A times C in this example is, you guys do the AC method. That's what I like to do. A times C in this is equal to 6 times -3, which is -18. And you think about the factors that multiply, the factors of -18 that would add to -7. Well, the factors of -18 are 1 and -18. Well, no way that's going to add to 7. Neither is -1 and +18, so those guys are no good. Another way you could get to -18 is -2 and +9. Well, that adds to +7, so we're close. How about 2 and -9? So those are our factors. So then I rewrite this as 6x squared plus 2x minus 9x minus 3, and now I use factoring by grouping. X minus 7. I'm going to first switch these to plus negatives because that way I won't mess up my factoring by grouping. Let me switch to another color here since I'm working inside here. I'm going to group the first two and the next two. In the first two, the common factor of 6x squared and 2x is 2x. That leaves behind a 3x. That would be 6x squared plus 1. Plus, the common factor in -9x and -3 is -3, which leaves behind 3x plus 1. All right, so that gives me x minus 7 out here. I have my common factors, 3x plus 1, and that is times 2x minus 3. So now I have completely factored my polynomial. All right, awesome. So now we can find all the other zeros. We had this one. This is the one we read off the graph, x equal to 7. This one's going to be, well, we need 3x plus 1 equal to 0. So 3x equals -1. X equals -1/3 is another 0. And that looks like it's this one right here. And 2x minus 3 equals 0. 2x equals 3. X equals 3/2. And that's what this one is right here. So what did we do with this problem? Let's recap. So what we did is we looked at the graph and we were able to read what we clearly could find 1, 0 by using the graph. That was 7. We divided off that linear factor, which reduced it to a quadratic. We know how to factor quadratics, so we factored it. And we solved it by factoring and setting equal to 0 and finding the other two zeros. We could have also at this point, if we wanted to find the other two zeros, we could have used the quadratic formula at this point too. That's always fine. You could have used the quadratic formula to solve for the other two zeros as well. That would be equally good. All right, let's try a little bit harder one. Same idea. So this one is going to have complex numbers. Remember that the square root of -1 is represented by the letter I, kind of a scripty I, and that I squared equals -1. So what we're going to do now is we're going to completely factor this polynomial given one of our roots. Now before, we got one of our roots by looking at the graph and reading it off. Now somebody's just telling you, hey, here's a gift. One of the roots is -1. All right, so we're going to use synthetic division to factor off that root. So we're going to use synthetic division. So 1x cubed, oh, I should draw my little bar first, minus 1x squared plus 8x plus 10, and my root is -1. So you bring the 1 down. 1 times -1 is -1. These negatives sometimes mess with me. -1 plus -1 is -2. -2 times -1 is 2. Okay, I think I messed up somewhere. Oh, no, I'm good. 8 plus 2 is 10. 10 times -1 is -10. 10 plus -10 is 0. Now, if you are given a root and you do the synthetic division and you don't get a 0 remainder, you probably messed up somewhere. And it's easy to mess up with synthetic division because it's such an algorithmic process. There's not really any conceptual understanding there. You're just working through it. That should always be a 0 if 0 remainder. If that's your remainder, that should always be a 0 when you're looking at a root. All right, so what does this tell us? It tells us that x cubed minus x squared plus 8x plus 10 equals x minus -1, right? That's this root, times, this is my constant term, this is my x squared, 1x squared minus 2x plus 10. All right, can we factor that anymore? Let's look at x squared minus 2x plus 10. This is a pretty easy factoring job. We needed to multiply to 10 and add to -2. Well, that's not going to happen, right? Because if we're going to multiply to 10, we could have either both positive or both negative. Since the cross term is negative, they have to both be negative. But to multiply to 10, you could take -1 times -10. That doesn't add to -2. Or you could take -2 times -5, which also does not add to -2. So this guy does not factor. Does not factor. So what we're going to do is say that this is completely factored. Okay? So completely factored form is going to be, I'm going to write it as x plus 1, x squared minus 2x plus 10. That is completely factored for this polynomial. That quadratic part doesn't factor. But what if we want to answer this one? What are all the zeros of h of x? Well, right now, when you're in your thinking, you should already be thinking, hey, these are going to probably have complex zeros. Because if it wasn't complex zeros, most of it would factor, right? So if it was zeros of like 5 and 2, we would have got x minus 5, x minus 2, right? But we couldn't factor it, so we must be thinking now something's up a little bit with these roots. Well, we know 1, 0 is x equal to -1. We were given that one, check. We need to find the other two, so we're going to use the quadratic formula. We're going to use the quadratic formula on this last factored part. Quadratic formula on this guy. All right, so it's -b, -2, plus or minus the square root of b squared minus 4ac all over 2a. Let's just double check that. Minus b plus or minus the square root, b squared minus 4ac all over 2a. Okay, so that's 2 plus or minus the square root, and that's 4 minus 40 all over 2. So that was a really long square root sign. Let's make them a little bit shorter. So that's 2 plus or minus the square root of -36 over 2. And that's equal to 2 plus or minus the square root of -36 is 6i over 2. So that breaks into two cases, 2 plus 6i over 2, or 2 minus 6i over 2. And we can take the 2 into both of these. So that's going to be 1 plus 3i, 1 minus 3i. And here's a little rule for you to remember. Complex zeros of polynomials always come in conjugate pairs. Okay, let me write that down. I'm out of space. I'm going to write it over here in black. Complex zeros of polynomials always come in conjugate pairs. What the heck does that mean? It's a big sentence. It means that if 1 plus 3i is one of your zeros, 1 minus 3i is going to be the other zero. Remember when you learned about complex conjugates? It maybe was a little bit ago. Remember if they have the plus or minus inside between the real and complex part, they're complex conjugates. If one pair of a complex conjugate is a zero, the other one will be as well. I don't have a ton of space right here because I meant to put an extra blank page, but I didn't. But just one quick thing. So for example, if we knew that 4 minus 3i was a zero, if you just knew that for some reason, somebody told you, then you would automatically know that minus 4 plus 3i was also a zero. Those guys come in pairs. All right, that's it for section 5.4.